Welcome back. In the last sections, we have talked about the most popular explanation for lift and their misconceptions, and I've also derived Bernoulli's equations for you, and we looked at curved streamlines, and now we are able to explain lift on aerofoils. So I've drawn the diagram here. So you can see these lines are streamlines. I'll consider moving along a line from point A here towards the surface of the wing and keep in a path that is always perpendicular to the local streamline direction. So do you remember the things we have talked about? The curved streamlines is the pressure gradient is always increasing in the direction away from the center of curvature. So you can see the curvature here is bending upwards. So you can easily tell that pressure at B is smaller than that at A, as the pressure gradient is increasing upwards. Similarly, as you move from a point D towards the C on the wing, and the line CD is always perpendicular to the local streamline. And you can see the streamline here is also bending upwards. So you use the conclusion from curved streamlines, you'll find that pressure at C is greater than that at D. The pressure at A and D are all equal to the atmospheric pressure. So you can simply find out the pressure at C is greater than that at B. So the net pressure, there's a pressure difference, net pressure is upward, so there will be an upward force, which simply describes how the lift is generated. Actually, any shape that can introduce curvature into the flow field can generate lift. And there's one weird thing about our popular explanation is it cannot describe when why a plane can fly upward down. As you can see, in reality, uh, the plane can flying can keep flying even though it's inverted. So using our theorem, it simply tells you that any shape that can induce curvature, which is the bending of the streamline, it can generate lift. So now we'll talk about the thick and thin aerofoil wings. As you can see, the streamlines here, streamlines above their surface are quite similar. It's bending upwards with similar curvature, but the stuff below them is quite different. So you can see for thin lines, the streamlines are mainly bending upwards as well. So there's higher pressure at the bottom, but for thick wings here, it's bending downwards. So actually, at this point, the pressure is smaller than the atmospheric pressure. So you really have to make sure that pressure at point B is greater than that at point C. So what we can conclude is the lower surface of the thick aerofoil doesn't contribute much to the resultant lift. Hence, thin aerofoils are better at generating lift. So you can see birds, their wings are quite thin. However, you might ask, what airplanes that do not have very thin wings? One thing is the volume of wing is also very important for commercial airliners. Is the volume contained in the wing also have useful functions. For example, they have fuselages in the wings. So it's not very thin, and it's not possible for us to make quite thin wings. So this diagram, this picture shows you how a plane can be flying upside down just to make sure there's a net pressure difference pointing upwards. Now here's some extension to aviation physics, which is about angle of attack. Angle of attack, or simply angle of attack A, angle of attack AOA, means the acute angle between the chord line of wing and the relative wind. So what is chord line? So this is the wing of an aircraft, and this one is called chord. So angle of attack is the angle it made between the chord line and the relative motion of the wind. Let me clear it. As the angle of attack increases, more flow curvature is introduced above the wing. So at first you increase the angle of attack and you got more curvature, so the lift on the wing will increase indeed. But after a certain angle, the curvature above the wing will be turbulent, so the plane gets into a state called stall, which the lift on the wing is insufficient to support it flying any longer. So you can see here is the equation for lift is a coefficient c times v squared half rho and times s. S is the area of the wing. You can see the relationship between angle of attack and coefficient c. It will first be proportional to the angle of attack, and after a certain value, which is approximately 15 degrees, it will start to decrease. And I think it's so much for this topic. A short summary here. I give you a correct explanation for Bernoulli's equation, and I talk about the streamline curvature, pressure, and lift. So some things you have to remember is the first one, larger difference or longer difference is not necessary for lift production. And the second thing is the fluid particles traveling along upper surface reach the trailing edge before those along the lower surface. They do not travel simultaneously. And the third thing you have to bear in mind is Bernoulli's equation, which means the pressure drops along a streamline, the velocity increases, and vice versa. And you have to remember that you can only apply Bernoulli's equation along a streamline. For curved streamlines, you should remember the direction of the pressure gradient is always pointing away from the center of curvature, and you can use these series to explain the lift on wings. And I hope you really enjoy this topic about wings.